Hi and welcome to today's midterm webinar of ECMWF Summer of Weather Code. It is the first of two webinars we organize, which are in this first half or after the first half of the coding phase. We will have today 5 projects which will present you what they've been up to and what they've done the first 2 months, and then also what their plan is for the next 2 remaining months of the coding phase. So before we start, I would just like to give you a short overview what ECMWF Summer of Weather Code is, and specifically also about this year's edition of ECMWF Summer of Weather Code. So ECMWF Summer of Weather Code is brought to you by the European Center for Medium Range Weather Forecasts in collaboration with the Copernicus services at ECMWF. And the idea of ESoC is to bring in open source innovations and software developments related to meteorology and climate, but also in the past years and also this year, we have a specific focus on machine learning, weather visualization, and also cloud computing. The idea or how the program works is that we have an application phase, which usually starts at the beginning of the year. And in mid of April, the application phase closes. Then we have around 2 weeks of evaluations. And then before 1st of May, we announce the final ECMWF Summer of Weather Code projects of this specific year. So this year we announce the final teams who are part of ECMWF Summer of Weather Code on 30th of April. And since 3rd of May, 9 projects are now working on the projects together with mentors from ECMWF and Copernicus. And the coding phase is still going until the end of August, until 31st of August. And there will be another opportunity also for you to join another webinar where you can see what the projects have been working on. It will be the final ESoC day, which is anticipated to take place on the 29th of September for now. So you can already mark your calendars or save the date. So we have this year 9 projects, in total 16 participants who compose of 9 teams. And the projects can be divided in 3 major topics. So we have projects related to machine learning, to software development, and to weather visualizations. And today we present you 5 projects which are marked here in orange. As I said, since 3rd of May, we are in the coding phase, and the coding phase is the core or the heart of ECMWF Summer of Weather Code. This is where all the innovation and open source development takes place. And one of the key features of ECMWF Summer of Weather Code is also that during the coding phase, the ESoC teams are teaming up with experienced mentors and experts from ECMWF and Copernicus. And so since 1st of May, the last 2 months or 2.5 months, the teams have been now closely working together with mentors. And today we want to show you how, first of all, we want to present you what the projects are about, and also what they did in the first 2 months. So what you can expect today is we present you 5 projects. The first project is from Varun Banka, who works on a ECMWF user dashboard. The second one is from Ashwin Samudre, who works on a Python library called ClimateLab, and he will tell you more about what this library aims to do. The third project is presented by Hetcha and Avistri Kare, who present you an application related to machine learning for land, and specifically a machine learning application to detect Earth heating patterns. The fourth project is related to weather visualizations, and it is presented by Tishampati Dar, Gicini Naguria, and Joshua Martinez Moreno, who work on enhancing the Blender software to make weather visualizations or to support better applications and weather data. And the fifth project is presented by Catherine Schmidt, who works on the project called Meeresvogel, and she will shed more light into what her project is about. Just some housekeeping rules. There will be some opportunity, or there will be opportunity for you, of course, also to ask questions. So each project is presenting around 8 minutes of what they are doing. And then for each project, there will be either directly after the presentation, some time to respond to questions, or at the end, we also have some time to collect all the questions, and then we have a bit of a longer Q&A. And we ask you to go to Slido and enter the hashtag ESoC 2021. And there you can ask all the questions you have to the participants and to the presenters today. And with this, I stop talking and I stop the introduction, and I would like to welcome the first presenter today, who is Varun Banka, and he will introduce or tell us more about his ESoC 2021 project, ECMWF User Dashboard. Varun, the floor is yours.
Yeah. So is my screen visible?
Yes, looks perfect.
Hello everyone, I am Varun, a computer science undergraduate from BITS Pilani, India. I hope everyone is doing fine and taking care of themselves amidst this global pandemic. For the past 2 months, I have been building a user dashboard along with my mentors, Helen, Sylvie, and Carsten, and also with the help of some incredible developers at ECMWF. And today I'm going to present my work to you all here. So this is the outline of today's presentation. First, I'll discuss about the aim and motivation behind the project. So just to get a full picture of what we are trying to achieve here. Then I'll move on to the technical details on how the project works and how is it structured. After that, I'll briefly discuss about what are widgets and show you a few of them. Then I'll share a few of the challenges that we faced during the development of this project. After that, we'll see a short demo of the project just to get an idea about what stage it's currently on. And lastly, I'll discuss about the future targets and how we plan to achieve them. So what's my project about? The problem we are trying to solve here is to build a single location for all ECMWF users, so they get a brief overview of various different services they use and interact with at ECMWF. So it's much like AWS CloudWatch dashboards, where you get a quick look of the services you use at AWS with the use of widgets. As large number of people use these services frequently, the main aim behind this project is to just simplify things for the user and improve their user experience as well as their productivity. Another aim of this project is to identify the key challenges faced during interfacing with various different ECMWF services, so this data can be used by internal teams during development. So really the big picture here is that this project reaches to a point where the user will able to have an overview of almost all the ECMWF services that they have access to. Turns out this is quite complicated to achieve, but with time, it can definitely be done. And that is why we decided to take a modular approach. Now, I'll go a little into the technical details and explain you the architecture of the project. I will explain the architecture using this block diagram. So the project uses React with TypeScript at the front end and Django as the application layer, and PostgreSQL as the database layer. So when the user adds a widget in the dashboard, it makes a request to the backend in order to get the required data. And this request contains an authentication token, which will be decoded at the backend to identify the user. Once the user is identified, the backend then makes a request to corresponding ECMWF server. This service may be public or it may require user authentication. But suppose if the service is public, getting the data isn't much of a hassle. In this case, the backend just acts as a proxy server and forwards the received data to the front end. This is done in order to avoid course issue, which denies the front end from directly making any request to ECMWF servers and get the data. But handling the case where the service requires user to be authenticated has been the biggest challenge of this project. For a few widgets currently under development, we found a workaround that is to use the API tokens in order to make a successful request. Once the backend makes a successful request, it does some processing and sends the data to the front end in the desired format. The interaction between the front end and the backend occurs through REST APIs. And for this, we use Django REST framework. The database here currently holds information about the user, access token, and dashboard layouts, and this state. So let's briefly talk about widgets and their role in this project. So what's a widget? Widget is basically a window of information that may be related to some service at ECMWF, or it can be standalone. So by now we have completed these following widgets, and as more widgets are built, we find a pattern to make them more uniform across, as well as extend them with different functionalities to improve user experience. There are widgets that are currently under development, and many more are planned. Every week, I, along with my mentors, take on a widget to implement, check its feasibility and challenges that may come. Then we see how those challenges can be solved, or if anything can be built internally to make it easier to build the widget. Recently, we decided to build a mass API widget, and a custom API was built internally so that my application could access the required data easily and display it in a widget. There have been fair amount of challenges while building this project and getting it to this point. Some have been solved. For some, we created a temporary workaround, and some still exist. I'll share a few of them with you. This project tries to interface with different ECMWF services. For example, services at apps.ecmwf.int or events.ecmwf.int or any services for that matter. But all these services have different architecture internally, and they are not built using the same technology. So there doesn't exist a uniform way on how the widgets can get data from these services. So we need to handle each of these cases individually. Some widgets which can access public data theoretically can make a direct request to ECMWF servers and get the data. But CORS prevents this from happening. Hence, the request needs to be rerouted from a proxy server, which in our case is routed from the backend. This does cause some undesired code duplication as well as delays. Also, ECMWF services were not built to be accessed by third-party services. So this project currently in its development phase basically acts as a third-party service trying to access data from ECMWF servers. So we need to find some workarounds or create custom endpoints for these services internally, which can then be used by user dashboard application to access the data. Initially, the application didn't have any login system or user session system, as we thought at some point this application may be able to share the common authentication system which all ECMWF services have. But it turns out the user actually needs to visit the service before they remain authenticated for the specific service. And even then, the session cookies are not shared, as the application is basically a third-party service. So I did implement a custom user session system in my application. Due to this, for now, the user explicitly needs to register in the application so they can identify uniquely. But even if the authentication problem is now solved for the user dashboard application, it doesn't mean that we solve the issue for ECMWF services, which require user to be logged in order to get the data. And this is one challenge we are trying to solve even now. Currently, we implemented a temporary workaround where we manually store user API tokens in the database and then use these to make the request to ECMWF services. This way, we can get users' data using the API token. Tokens are automatically generated for every user. So to some extent, this technique does work. But with all this workaround comes the issue of security. We want to securely store the user tokens and not somehow expose them to the front end or somewhere where others can find them. Despite multiple challenges, we have made progress. So let me share with you a short demo video that I prepared to showcase the widgets and the user dashboard. So we have an idea at which stage the project is. So first we'll look at the chart widget, which you can add by going to the chart browser and just selecting any chart you want. And once you add a chart, you can move it, shift it, resize it, arrange it the way you want it. And then you can minimize the title bar, you can expand it, you can look at different times, and you can also look at the labels. And then you can get a quick information about the chart. And you can as well also go full screen to analyze the chart more closely. Now let's look at another widget. Let's look at events widget, which can be added through this menu. And once added, you can again move it, resize it. You can arrange it however you like it. And the loading screen you see here is the widget requesting the data from the backend. And once the data is received, it will show you the events. And you can resize it to your liking. So I'm just extending it till here. And then you can view the events. And if you want more information about the events, you can click on the link and it will take you to the events page, which will show you more information about the event. And you can also, I guess, register here. Now let's look at service status widget, which will show you the status of different services at ECMWF. And you can get more information about them if they are down or something. So it will take you to this page. And now let's look at satellite alerts widget, which will warn you if any warnings are present. It will be highlighted in reds, which you can further inspect the instruments by clicking on the name. And again, by the way, you can always remove the widget and add it right back. You can also move it like any other widget. Let's now look at the text widget, which you can also see how resizing and adding widget can affect your layouts. So you can use this widget to add any note or ideas you have. It supports rich text editing, so you can bold it, underline it, and it will stay persisted in your dashboard. So let's add another chart. So the dashboard looks the way I want it. So you can again add a chart from the chart browser. Let's select some random chart, and you can resize it as it's loading. And so this way you can create a dashboard to your liking using the widgets which are important to you. And finally, you can remove all the widgets as easily as you can add them. So yeah, so that's a short demo of what we have achieved till now. It is still work in progress, but slowly as it comes together, will provide a seamless experience to all the users. So what's next? Our first target will always be to build more useful widgets for the users. We have plans for many widgets, but it all depends on their feasibility. Our second target is to make application more uniform and intuitive for the users, improve the speed, and generally make it pleasant to use to enhance the user experience. Then we still need to overcome certain challenges regarding authentication and security. Finally, the end target of this is to complete. Finally, the end target is to complete the application with proper documentation and test and write a Docker file for its containerization. So that's it. I conclude my presentation here. I would like to deeply thank my mentors for their immense support and dedication and solving any doubts I had. They are truly amazing. So that's it. So if you have any questions, feel free to ask them. I'll be happy to answer. Thank you.
Thank you, Vagun. This is amazing and impressive work. Before we go, I think we have one question from Frank. He says the UI looks nice. Where do you store the dashboard state, locally or on the server?
So we store it in the server in a database. So the user can relog in and get the same data dashboard again.
Okay.
So every time make any change to the layout in the dashboard, it will send an asynchronous request to the dashboard and it will store the layout.
Okay, perfect. Thank you. So thank you, Vagun. And I would now go to the next presentation. I would like to invite Ashwin Samutre, who will tell us more about the Python package ClimateLab. Ashwin, the floor is yours.
Sure, thanks. Varun, can you please stop share? Yeah, thanks. Okay, so can you see my screen?
Yes.
Okay, yeah.
Maybe in full screen, then
sure.
Yeah.
Okay, yeah. So hello everyone, I'm Ashwin, currently a research assistant at Simon Fraser University. And as part of this year's ESoWC, I'm working on ClimateLab project along with my mentors Bodwan and Florian. So ClimateLab is a Python package with 4 main functionalities. It provides easier data access to the climate and meteorological datasets. It works on the processing of these datasets like format handling, the data loading, the data rollers that we have to write. It also works for the interoperability of these datasets. So say you want to have these datasets to be loaded with Jupyter notebooks, then you have SciPy Stack to handle datasets such as NumPy, Pandas, and all. And also the machine learning frameworks such as TensorFlow, Keras, and PyTorch. And after this, you have the output from this data science or machine learning project pipeline that you get something such as a trained model, and you need to do inference over that. So you get to have some form of graphs and curves such as training curve, the loss curve, and many more. So ClimateLab aims to act as a one full package which can provide all these functionalities. It also has this plugin architecture, so that provides easy addition of data sources, data sets, and plotting styles. As part of this project, like for this 4 months, I'm keeping the scope to these 3 things, mainly adding a matplotlib driver, adding index source plugin, and working on ZAR format for large-scale data storage. This is an experimental part since it involves many experiments to try out with different size of data sets and different compression formats and all. So I'll be presenting that as well. So again, yeah, so the main project goals involve these 3 things that I just mentioned. So to extend ClimateLab so that it seamlessly interfaces with Intech and allows users to access all Intech compatible datasets. This involves CSV files, NetCDF files, GRIF files, which are mainly relevant to the climate science community. Then second would be the extend ClimateLab so that it offers user with high-level matplotlib-based plotting functions. This is really important when we are going with machine learning, like the projects in machine learning community are mainly based with matplotlib as the plotting library. So currently ClimateLab is based with Magix, which is a go-to package for many of the ECMWF software set. But we want to add matplotlib so that we can have this plume plots, ROC curves, the training curves as an additional function. And then we want to try to compare the data format ZAR with the NetCDF and GRIP format, and to see how it performs with small scale as well as large scale data sets. So as I mentioned, these 3 tasks are divided in. So for the first task, this task is completed for now, as part of from when I started working till now, this part is completed. So this is what I'm doing here is mainly Intech provides. So previously ClimateLab had the data sets to be added as just you had to write your own data format, how exactly you are gonna get that. So say the data extension, if it's a CSV, it's an HDF, and this had to be done. So but with Intech, you can just import ClimateLab CML, and then you just load data. It calls the Intech package that is currently being added as a plugin. It's added as a source plugin, and then it infers what kind of data that you are trying. So you don't have to handle that functionality anymore. So it does that for you. This package is released on PyPy, and it can be installed via pip. So it's ready to use. And it provides currently the support for CSV, NetCDF, ZAR, GRIP, and pickle files. So this is mainly we are going in the direction of machine learning projects. So moving ahead for the second task, which is mainly around the matplotlib thing. So Magix is currently the go-to package as part of ECMWF suite of softwares for plotting. But the machine learning specific graphs can be handled better with matplotlib. And since Magix is a package for is being there for a long time, it's there for mainly to handle the climate the data sets functionality, but not specific to machine learning things. And that's why we are trying to add matplotlib here. So in the short term, matplotlib integration into ClimateLab for plotting functionality from ML point of view with use in Jupyter notebooks. And in the long term, with further development and adding more functionalities, it can be as good as Magix, so that we can get all the functionalities which are currently present in Magix with matplotlib. So this will require more and more development, but currently we are focusing on few important things which are relevant to the machine learning projects. So yes, so currently the setup in ClimateLab is you get the plotting functionality with a driver, which is currently Magix. It calls the action package, and then it calls the plot figure module. What I'll be doing here, and currently I'm working on this is a work in progress. So what I'm just adding, I'm providing the user to have 2 drivers as the options. So one would be Magix, another would be matplotlib. And these actions would be selected based on what the curve you select. So say you want to plot the training error curve. So the driver would be matplotlib, since Magix doesn't have that functionality yet. And then it can be done with that way. So next, I'm just showing it. Here is a figure which was previously done via Magix, but now it's being plotted with matplotlib. This is for the sea level pressure field. Then another figure, which is for the precipitation field, which was previously done with Magix, and currently we are able to do that with matplotlib. Okay, so moving to task 3. Okay, mainly we get data sets like the climate and weather related data sets are of different sizes. So for small scale data sets, the conversion between different data formats is really trivial, and there are many APIs available for that. So here I've added 2 examples. So first, if you look at, say, an HDF format to be converted into ZAR format, what you do is you just load Xarray as XR, and you open the data set, and then you just convert it to ZAR. Also, for GRIP format to be converted into ZAR format, you just load the data set with Xarray, and then you just convert it to ZAR. This is really easy and possible for small scale data sets. But when we are moving to data sets of huge sizes, then it's not really that feasible. And that's why we need to move to we need proper methods to how we are going to convert this data set into ZAR format. The main concerns with data storage are can be summarized as this 4 points. So we need multi-threaded parallel read and write when we are handling data. We also want to avoid swapping via chunking strategies. So what we mean by chunking is that we should be able to store the data in the form of chunks so that it can be easier to access, and instead of having the swapping thing. Then many of the times when the data sets are stored on, say, on server or mainly like cloud-based storages, compression and decompression happens so that data sets can be stored efficiently. But this compression and CPU time is required to this compression and uncompression. We need to reduce that. And again, the performance, local performance is okay. We can do that. Once we download a data set, we can have it locally and just load it and all, but it's not feasible all the time. So most of the data sets are stored on cloud storage. So we also need good functionality to handle those as well. And that's why we have to have a format which can work well with like considering all these possibilities. And that's why we have different, like currently I have tried to compare what we have with NetCDF Grip and what we can get with ZAR. So NetCDF and Grip are most widely used formats, like for the archives of climate science datasets. The storage formats for these files are based on NetCDF binary format and SDF5 format. And this provided effective disk storage in the past, but it does not work really well with cloud storage. This claim is done from the recent work that is done by the Pangeo community. Pangeo community handles this climate-related data set, and they have their own framework for that. And they have performed this study on how we can move from, they're also trying to move from NetCDF to ZAR. So this is the claim from their study. And also, in order to read a single variable or metadata, whole file read is required. So this is a really inefficient thing, and we don't want to do that. This happens mainly due to the opaque nature of these files. Also, the NetCDF and Grip formats are ill-equipped at handling the concurrent data access. So there are many issues currently faced with NetCDF and Grip. So that's why the ZAR format is a really good one, and it can be a good replacement for NetCDF and Grip. ZAR provides us with parallelism, so it has this multi-thread and multi-processing thing. It helps for the data storage in chunks, so you don't have to have the swapping thing, but you can just go for the chunks of the data, and so you can access them at once instead of going step by step. Then the metadata with ZAR format is stored in one place, so it gives us a single read operation instead of the multiple read operations that we had to do for each variable. We had to do multiple single operation in NetCDF format. ZAR arrays are mainly stored as key values, key value thing on object storage systems, and as a hierarchical directory store on POSIX file systems. This provides a really good way to access the data. So for the POSIX file systems, we mainly have this hierarchical directory, and that can be a good replacement for what we have with NetCDF and Grip. Also, the chunk functionality provides reliable use in case of the data transfer. So when we are, as is mentioned in the next thing, so say we are trying to get data from a server or from cloud-based storage, and the connection drops. So you can just pick up the last chunk of the data already written and continue the retrieval process with just one append option. This is one of the good functionalities that is really important, since there can be network issues that arise when we are trying to get data, access data. And that's why these are some of the functionalities from ZAR, which I studied while creating the proposal of this project. But that's the point of that would be the next thing. We'll try to explore many more things possible with ZAR and see how it can be done, how it can replace the NetCDF and Grip formats. Okay, so the major subtask for this task would be to compare ZAR, NetCDF, and Grip. Then test the sequential as well as asynchronous operations on large data sets. We'll be deciding different size data sets, and then we'll compare how ZAR performs for the access, for the read write, and all these things when compared to Grip. We also want to try with different chunk sizes for the multiple data sets. So there would be we want to see if it scales well if we go for larger chunks, or it scales well only if the chunks are small. So that is something to be seen. Then the data compression is a factor that, as I mentioned, data compression plays a major role in data access, and it provides a set of data compressors. So you can select which form of compression you want. And so what we'll try to do here is to use these different compression techniques and benchmark the performance as can be shown with, and useful for the results based on the data. Also, there is another format named N5, which is similar to what we have in ZAR. and it handles the data in similar way. And there is a combined format which is given. So we'll be seeing if we can go with ZAR and N5 as well. And that would be the next step. Like once we are done with this comparison, we can also try to see if N5 is a good thing to do. So this is part to be done, and this is mainly an exploratory work. So this would be how some form of kind of a little research thing to do, like as I mentioned, different chunks, different compressors, and all these things, so that we can actually benchmark on how good ZAR is if we are really want to move from NetCDF and grep to ZAR. So that's part of the thing. And yes, so that's it for now. And I'll be happy to take any questions if you have. Thank you.
Thank you, Ashwin, for explaining more about ClimateLab. And I think it will be very helpful for many machine learning projects. And I would also specifically say specifically also for the next project we want to present you. So Hetcha and Avishri Kare, they work currently on a machine learning project trying to detect the Earth heating patterns and working with a lot of weather and climate data. So maybe you could also have a look to the ClimateLab. But for now, I would invite you to the floor and looking forward to your presentation. Avishri and Het, the floor is yours.
Thank you, Julia, for having us. I'll share my screen. So I hope it is visible now. So today, I, Hetcha, and my friend Avishri Kare are going to talk about ML for land, which we have been working on for the past 2 months. We would like to take a moment to thank all the mentors for the constant support that they have given. Without them, we would not be able to do what we have done so far. So before talking about the problem itself, we would like to understand why this problem exists and why are we interested in solving it. So we are making a study on land surface temperature, which is the radiative skin temperature of the Earth's surface. Land surface temperature is used to understand the heating patterns of the Earth's surface, which could be from different periods of time. And it could tell us how different regions of the Earth are heating throughout the time period. Understanding this heating patterns could also lead us to understand various other patterns as well. For example, land use patterns of the Earth's surface. Moving on. So is there any solution or a tool that actually helps us in predicting land surface temperature? Turns out ERA5 has a reanalysis tool, which provides us with the skin temperature. But there are some shortcomings with ERA5 skin temperature. It is at a coarser resolution of 31 kilometers, which is not something that you would want. You would want our solution to be having a very high resolution, for example, 1 kilometer or 500 meters. Skin temperature can sometimes be not as accurate as land surface temperature, which is predicted by the ground truth satellite observations. And thus, we would want a system that is effectively able to predict the land surface temperature at a very high resolution. So let's move on and formally define the problem statement that we have. So the problem statement is that we have to learn a mapping from the modeled world, which is the ERA5 in our case, to ground truth satellite observations, which will provide us land surface temperature. We use NASA MODIS data to provide us with the land surface temperature values. This resulting tool that will learn the mapping that between the modeled world and the satellite observations will also help us understand many other things as well. For example, it will help us understand what variables are actually affecting the prediction of land surface temperatures and how the change in these variables and the values of these variables are going to affect the changes in the values of the land surface temperatures. It can also help us detect places where the observations and predictions are differing significantly. And this could be due to various boundary or edge cases, for example, natural calamities, forest fires, and other calamities like these, which can change the values of land surface temperature significantly. So overall, in an overview, we would want our tool to take in ERFI variables as an input and give out land surface temperature as an output. And to do this, we take NASA merged data.
Okay, so now that we've understood the problem and the motivation behind it, let's take a look at how we actually plan to achieve it. So we've divided this into a 4-part process, starting with the first and the most important part of data collection. So we would need to collect important variables, including ERA5 reanalysis variables for input, MODIS LST variable for output, and the ERA5 skin temperature values for comparison. All of this data needs to be collected and appropriately pre-processed before it is fed to any ML model. The second part of the process would be to estimate land surface temperature for individual sites or for points on the map. By doing this, we understand how easy or tough it is to actually predict land surface temperature and which variables, or rather which input variables, would be the most important in predicting land surface temperature. Once we have a smaller set of input variables to look at, we could move to a larger scale, that is from points or individual sites to states, cities, countries, and continents as a whole. And we could build models which would then help us in estimating land surface temperature. The final and the most ambitious goal, which we do not aim to complete as a part of this project, but which would be the ultimate goal, would be to predict land surface temperature for the entire globe. So, so far we have looked at the first 2 steps in this process, and we would be starting with the third step soon. So let's take a look at the machine learning pipeline used for this project. So as land surface temperature is a real valued variable, we would be modeling it as a regression problem. We would have some training data from step 1 in the previous roadmap, and using that to train an ML model. This ML model would then predict some land surface temperature values, which can be improved by calculating relevant errors with the actual MODIS ground truth values. This error can be propagated back to the model so that it understands how to make better LST predictions in the future. Once we have trained the model substantially, we could then use any new data or testing data and provide that to the ML model. Once this data is provided to the model, we can expect the model to actually output some accurate LST predictions for this new data. So this is a generic ML pipeline, irrespective of how you want to, or which scale you want to predict LST for. That is irrespective of point, regional, or global estimation. However, we've looked at point estimation so far, and we'd like to provide some details on that. So for point estimation, we considered 10 European sites, both for training and testing data. For the months of February and August, the entire data set comprised of data from the year 2000 to 2021, and it was divided into training and testing data, such that the training data had all the data points up to 2018, and from 2019, we have the testing data. For the ML models, we considered linear regression, random forest, and other similar simple ML models in order to predict land surface temperature and also understand which input features are the most important. So this was not an easy journey so far, and we have come across certain challenges. The first major challenge was that the ground truth data was insufficient. That is, the MODIS LST values were not many to begin with. In order to solve this, we imputed the missing values by taking aggregates from neighboring locations around the site. So we build a bounding box around the site, and we see if there are any MODIS LST values and aggregate them to actually report the value for that given site. This resulted in a 57% increase in the number of data points, and more data equals better models. So this was definitely a good starting point. The second challenge that we faced was that there was a lot of difference in the time scale of ERA5 reanalysis variables and MODIS land surface temperature. So ERA5 variables are present on an hourly basis, whereas MODIS provides daily values for land surface temperature. In order to bridge this gap, we aggregated ERA5 hourly variables to report daily aggregates and used these to build a day-wise model. So our model predicted land surface temperature for a given day using input aggregates from ERA5. Another challenge that we faced was to incorporate sufficient regional representation. That is, we didn't want to have sites which were all of the same type, as that would not help in learning much. In order to solve this, we considered a balanced set of urban and rural locations. More specifically, we had 10 European sites with 4 diverse dominant land types so that the model has enough variety to look at and can learn better. So coming over to the most interesting part, which are the results that we've seen so far. So the first important result is that whichever models we built, so the best models that we had were better than ERA5 skin temperature values. More specifically, for a model built for all the locations that we saw a 1 Kelvin lower root mean squared error. That is, we were more or less 1 Kelvin closer to the actual values than ERA5. And a model built specifically for a city of London, we saw a 0.5 Kelvin decrease in the root mean squared error. So here is a brief comparison of ERA5 skin temperature and our model predicted LST values when compared to the ground truth data for London in the month of February 2019. So the orange line represents our model predictions and the blue line represents ERA5 skin temperature. And we can see that the orange line is closer to many points as opposed to the ERA5 skin temperature values. The second important result from our work so far has been to find the important features which we can use to build a regional model later. We saw that irrespective of the number of sites we picked, we saw a very consistent set of top 5 features. That is, the top 5 features were more or less the same across locations and across months. A very important observation was that 2 meter temperature was the most important feature. And that is consistent with what we know from analysis. Here are the top 5 features that we've seen for some cases. And we wish to refine this list so that we are sure that these are the actual features that affect prediction. So that's what we've done so far. And later on, we would be wrapping up on point estimation. That is finding a more crisp list of input features that would be more helpful in predicting land surface temperature, and then extending this to find LST values for a given region. Being more ambitious, it would be the entire continent of Europe. And we hope to present that the next time we see all of you. Again, once again, thank you for giving us this opportunity. And we hope you like our work. And we are open to any suggestions and questions now. Thank you.
Thank you, Avishri, and thank you, Het. Very impressive work so far. And yes, I agree. I also look forward to your results by the end of ESoC. We have 2 questions on Slido. So the first one is a suggestion and a question. Would using MODIS satellite pass time over the area of interest be feasible for better temporal match using something like pi orbital?
Yeah, so if I understand the question correctly, using temporal relations between the data, will it be helpful to understand the land surface temperature or not? I think yes, and we are planning to do there's temporal relationships between the data as well when we move on to regional prediction, because we think that that will be a challenging task over there.
Okay, and the second question, how well does the point-wise data adjust to a linear regression? Have you quantified which model represents better the data?
Yeah, so we have tried a few models. We have tried a few models, as said by Avishi, linear regression and random forest and other models as well. And as per our analysis that is done till now, we think that random forest was performing the best, and we are still looking at other models as well. So that is upcoming for the next presentation.
Okay, so thank you again, Avishri and Ed. I would now move to the last two presentations, focusing more on better visualizations. And the first presentation is from Tishampati Dar and Josue Martinez Moreno, who work on the project Blender NC enhancements. And yes, Tishampati and Josue, the floor is yours.
Thank you. So I'll share my screen. Just make sure the presentation is working okay. So, yep.
Yes.
Cool. Okay. So, yeah, I would like to thank Stefan and Sylvie. Gishini can't make it today. We are a distributed team. Yoshua and I started together in Canberra, but now I'm currently in Adelaide, and Gishini is in Nairobi. So we are in all different time zones. So yeah, this is a story of Blender NC software journey. I put together the slides, and Yoshua added some nice videos to it. So I think there will be some visualization content here. So the question is, how do we visually communicate climate and weather simulation data? You can create nice realistic views of what the Earth looks like at different times and show the dynamics of it, create what we would call a digital twin of the Earth, and show it to people, and people can get this, what astronauts normally get, the overview effect of seeing the Earth live and changing, and appreciate the planet. So the project has seen a lot of work from Australia recently, and I have contributed little bits and pieces of guidance and suggestions, and I guess making slides and writing issues on things to do. Gishini is looking forward to adding some forecast data into it. So Blender NC produces visualizations like that, the one you saw. And we have a couple of bigger ones here to show. And this one is showing some temperature visualizations with cloud heights included. And normally in a package like Magix or Matplotlib, it would be a flat visualization like this, and you can animate that to a PNG. If you want to display it in a global context, you will have to overlay this on the globe. And Blender NC does that using Blender's 3D rendering engine to actually use a UV sphere and use displacement and textures and bump maps to give you a much more realistic and rendered view of all the data that's available. So here that there is a transparent sphere outside with the clouds with displacements according to height, and then an internal one mapped to the temperatures. We have another one. This one is showing ice and salinity, and you can see the dynamism of it, variations. Things disappearing and reappearing seasonally, and then internal microstructures and movements. Shue is an oceanographer. So a lot of the visualizations that he previously built are based around oceanography. I am more an Earth observation person. I work for Geoscience Australia, which is an Australian Earth observation agency. I will share the story of how we came to find each other and work on this together in a minute. So yeah, so that's the story of how we came to start this project. It's this presentation you will find is slightly less technical than the other presentations and has, I'm an engineering manager, so has a more storytelling aspects to it. So I followed ECMWF on Twitter, and due to other work I was doing around live observation of rainfall in Africa, and I found I was consuming ECMWF forecast data at the time to compare our rainfall captured and the actual forecast. I found the project when the ECMWC was announced, and I was rooting around in the Blender NC source code. So it specifically said we would like to enhance Blender NC. And I found that references to Gaudi, which is a supercomputer here in Canberra, not here in Canberra, was in Canberra at the National Compute Infrastructure, and realized Josué was in Canberra. So I caught up with him, and Gishini was collaborating with me from Nairobi on the weather observation system. So brought him along. He had actually subscribed to ECMWF forecast data feed to look at the weather data, and I wanted to have that visualized in Blender NC as well. So yeah, to support the grid format we were receiving the data in. So yeah, I just put a proposal together, and the proposal essentially addressed what the task was, to improve the documentation of Blender NC, improve all of our coding practices, continuous integration, continuous delivery pipelines, for ECMWF specific purposes, add support for the grid format, and also create some of these interesting animations using the forecast and real analysis data that is available in grid format, and possibly in the future, as other presenters were saying, in ZAR and other formats as well. So previous to this work, Blender NC, as the name suggests, only supported NC or netcdf files. So now we have support for GRIB and ZAR once the huge PR that Josué is working on lands. Yeah, so we have added many features as we have improved. So the progress so this is another visualization of like a digital twin aspect. So the progress has been huge. If you look at the number of commits in the development branch, the amount of features and small fixes and big fixes have been added are huge. So you can, using the ECMWF data, reanalysis data, create digital twins of how things actually were at a time in the past, which is very impressive. I sometimes think of the weather simulation stuff as having sort of a time machine, looking forward and looking back and seeing what the Earth is like. So one of the tasks was to improve the Blender NC documentation. This is the Blender NC documentation page, hosted in Read the Docs. It consumes a GitHub repository and puts up the documentation. So we have added new screenshots, and there is a bit more work to be done. So the Blender NC documentation goals were to make it easier to adopt Blender NC to visualize your data. You would not default to using standard plotting packages or using an off-the-shelf tool. So you would have to have good instructions in installing this on top of Blender, through the available locations, available repositories, the Git repository or the Python package repository, because Blender NC is a Python package. Provide the simple possible working examples, and provide the data and add-on usage instructions. So we have a small XKCD illustration here because a tool which has no documentation, or the documentation needs a documentation, creates problems. So ideally, the interface is good enough that you solve the problem at hand without having to read the documentation. It's intuitive. Blender is a quite difficult to use tool for doing 3D graphics, and adding more difficulty using on top of Blender NC will put us in a worse position. So we are sort of in a tool that needs a manual stage once you are familiar enough with Blender. So there are still more work to be done for the examples to be created, the simple animations, adding the sphere, loading your files, and a lot of the 3D animation creation, especially in Blender, is an artistic exercise as opposed to as well as a scientific exercise. So how you want to do your storytelling and moving around and your camera views and the amount of, what would I best say, drama you want to add in your story, in the visual story, is important. We also are looking at the coding practices in Blender NC, so the CI/CD pipeline. So there was when I started looking at it, it was a mix of GitHub Actions and Travis, and there was not a lot of code coverage applied, which I'm really passionate about. And Sylvie mentioned some concerns around support for different versions of Blender. So we ended up working a lot on the Blender NC CI/CD pipeline to add a lot of GitHub Actions to perform the builds, publish to PyP, and a lot of them. So you can see the specific improvements here. So we added continuous testing, continuous integration using Docker container, which Blender Docker container is actually published by the New York Times. So I guess New York Times uses Blender for some of their visualization work as well. So migrated the CI pipeline to GitHub Actions completely, consistent code styling, implemented coverage testing. Previously, there was no coverage testing. So different version supports for different versions of Blender using GitHub matrices tests, which basically you can say test different versions. And as long as the New York Times Docker image exists for it, you can test against that Blender version. And also to ease installation, you can publish the packages into PyP. So someone in Blender can pip install Blender NC to get that on. So we automated a lot of our testing so that we could ship new features. So once you have automated it, you get more free time, or you can do more work out of it once you have removed any doubts around, will this really work? Otherwise, things get, as everything you add, you break 3 different things. So these are the different workflows in GitHub Actions that have been added. I really like the one that Joshua has added, where it uses the pre-commit to automatically fix your code. It makes the code commit on top. So I always forget to run pre-commit or install the pre-commit for a new repository, and it breaks on CI. So if the CI can fix my code, then that reduces a lot of work upfront. So we had very low coverage, or no coverage. There was no measurement of the coverage, but now we have almost 70% coverage of the tests on the Blender NC Python code base. Some of the visual testing, because Blender is a graphic tool, is difficult because we are testing in a headless mode in the continuous integration pipeline, but well, things will get better as we add more unit tests. Yeah, so presentation is relatively short. In conclusion, we have done a lot of work in improving how the Blender NC code can be done. We have started supporting the GRIB format. Now it's more fun part of actually utilizing it and creating some interesting animations using some data we get. Possibly improving reading of the data through ZAR or whatever new partitioning things we find that will let Blender read the data. Attempting to read very large data sets into Blender will be difficult. So we may need to look at some of those things to allow scalability of the rendering and multi-scale rendering possibly, as well as some of the headless rendering aspects of it for producing similar stories on a regular basis. Yeah, so happy to take any more questions.
Thank you, Dishampati. Thank you, Joshua, for sharing the great work you've done so far. It's, as you said, like for now, it's a lot of in the background, which can't be seen, but now we're also looking forward to the visualizations you will show us at the end of ESoC. And yeah, I would, so we don't have a question yet, but maybe later. And I would now go, because we're also already a bit over time, but thank you for staying with us. I would like to introduce Catherine Schmidt. She will present us her project called Meeresvogel, and she will tell us more about what is actually behind the project. So Catherine, welcome, the floor is yours.
Thank you. I'll just share my screen. Right, are we in business? Thanks very much, Julia. My project is called Meeresvogel, and I've been working with Stefan Seaman and Ian Russell, and I thank them for their patience and all their help. So Project Meeresvogel addresses a problem that I think the last project has also alluded to slightly, and that's that so many stories in the world have a weather-related component that can be more related with the help of graphics. However, there seem to be two extremes. Either the scientists are working with the really complicated systems for doing very detailed and technical graphics and illustrations. And then at the other end, we see a lot of, the public see a lot of sort of mass media weather forecasts, which are kind of, for the most part, very simplified and kind of get rid of a lot of the detail and, do the job they need to do. But it leaves this space in between where people want to talk about things, not necessarily weather stories, but stories that have, in which the weather plays a big role. But they don't have a way to easily produce the graphics that will help them communicate those stories. So my project has been exploring a potential solution to this. There won't be just one solution, but this is hopefully one of many. And it's a Python module that will help people to create these graphics easily without having to learn all the details of a tool like METView, which is an extremely useful and powerful tool, but does come with quite a steep learning curve, especially if you're not already kind of trained in meteorology or other geo-earth sciences. And just as a note, for the mystery of the name Meeresvogel, I just wanted to have a nice name, and Meeresvogel means a seabird. So the idea is it both incorporates the letters of METView and Google Earth into the word Meeresvogel, and also it has a nice image of a bird that can sort of skim the waves and see things from above on the ocean. Although I hasten to add, I'm not only concerned about visualizing ocean weather. I do hope that I can get together with some people that have stories from the earth to tell from the land. But just a bit of background on why I want to do this particular thing. So professionally, I'm a web systems engineer, and I have a passion for telling stories with data. And two of my favorite jobs have been in the area of meteorology, and at both ends of that spectrum I was talking about. So I worked as the head of the technical team on new media for the BBC Weather Centre. And at the same time, I worked on the web, not at the same time, later on, I worked a couple of years at ECMWF in the web team at the very scientific and technical end of producing visualizations for weather. And then recently, I've started working part-time as a journalist for sailing media. And so I do find myself wanting to tell weather-related stories about sailing races, and it's been quite frustrating finding an easy way to do that. I'm also, sort of my personal interests include sailing, in particular offshore ocean racing. In fact, I left ECMWF in 2013 in order to take part in the original single-handed transatlantic race, which is a solo race 3,000 miles across the North Atlantic, which is not undertaken lightly. Recently, I moved to the Atlantic coast of France in order to be in a place where I could better combine my personal and professional interests. So the example that I'm working on for my project is, as a demonstration of how a tool like this could be useful, is to tell some stories about the Vendée Globe race. And for those of you who might not be aware of it, the Vendée Globe race is a 4-yearly non-stop solo around the world yacht race, which starts and ends in Les Sables d'Olonne. The last version edition started last November, and the last competitor finished in early March, but it generally takes between 80 and 120 days. And during that time, the skippers are sort of 24/7 in race mode. It's sort of like running, 4 marathons a day for 80 to 100 days. So it's quite a superhuman. I mean, I don't think there's any kind of sporting event that comes close to requiring that sort of physical effort. But on top of that, these skippers, are managing these 60-foot boats. They're having to look at, download weather information a couple times a day and plan the route. And then also, as of the last edition, they were required by the organizers to be creating videos. So sending back at least every couple of days a short video, talking about what's been happening on their boat during the race. So this event is followed online by 11 million fans, and across France, you just can't get away from it. They claim that there were 193,000 pieces of coverage about the last edition of the race alone. So it's a big deal, and it's a lot of fun to follow. And if you're sort of interested in the weather side of it, the official website has a tracker, and it shows, as you can see here, that some weather information, which is basically just, I suspect, GFS 10-meter wind, which is great and really useful for understanding. But as anyone who's done any sort of ocean sailing will know, there's a lot more that affects how you race the boat than just the wind, or at least just the sustained wind. So there are things like gusts and sea state, waves. When you're in the tropics, the Cape parameter is quite useful to help you figure out where the thunderstorms and sort of convective systems are likely to come and bite you. And then when you get close to the south, towards Antarctica, you're starting to worry about sea ice, which is something that the organizers are quite concerned about, to the extent that they have set up an exclusion zone where the boats are very strongly penalized if they stray into the ice zone. So what I'm doing so far is building a proof of concept demo, which is essentially a bunch of scripts that deal with downloading the ERA 5 reanalysis grids from the Climate Data Service, and use those to create overlays for the parameters of interest. And what I'm outputting here is KML files for Google Earth. So you can go into Google Earth and you can sort of turn on and off the various sort of layers of interest that you want to look at. And at the same time, I have a script that creates a track for each boat. And each of those can be turned on and off as, as the user is, if they're just interested in one boat, or or a couple or all of them. It's up to you which ones you want to see. And then one of my scripts creates mouse overs for each path. So for the fields of interest, it will go and create sort of the KML markup to allow you to mouse over and see sort of what the wind was doing at every point on the track and what the waves were like, etc. And then finally, to sort of make it even more interesting, the skipper's onboard videos will be given as links along the track, so you can sort of watch the videos of the skippers and what they're experiencing, but at the same time have the context provided by the overall experience of sort of showing what the weather is doing on the globe. So that's what I've done so far. So for the future, once I have a kind of slightly more polished demo, I will share it and try to see who's interested. So I'll be sharing it with people like other sailing journalists or the media teams of the race teams or the media team of the actual event. And then there are a number of teams that had collaborations with scientific teams where they were taking measurements and observations of things like sea salinity and temperature as they went round. So it might be the case that they'd like to use a tool like this to disseminate their results to the general public. So not in terms of scientific or academic type communication, but communicating with the sort of general public. And so after sort of sharing it with them, I would hope to get some feedback and make changes in response. So, so for example, there might be parameters that I've not considered that would be of interest to some of these parties. So for example, at the moment I'm showing on this slide a chart of the Benjamin Fear Index, which is a fairly little known available parameter that is a kind of measure of the likelihood of rogue waves. And apparently it's used quite a bit by professional ship routers. But as far as I know, it's kind of not really known about within the ocean racing community, and it might be something that could interest them. So once I sort of make those changes and get the feedback, the next step is to actually turn it into more of a product, document it, and make it easy for other people to pick it up and use it. And as I said, I'm interested in seeing other possible uses in other domains, especially those on the land versus just on the sea. And I'd also be interested in exploring other outputs formats. So this particular event is a global event, so it makes sense to be looking at it on Google Earth on the whole globe, but there might be other events which are have a much smaller range, geographic range, which would be better off done in something like Leaflet.js. So, to be embedded in a web page. So that's where I'm at, and I'm kind of really having a lot of fun doing this and looking forward to getting, sort of getting it out there and getting feedback and seeing where it goes. And that's me. Thank you very much.
Thank you, Catherine, for sharing your project. And I specifically also like that you also found ECMWF Summer Weather Code, and you are able to combine your professional and personal interests. So very nice to see, and thank you for your presentation. So thank you for everyone for staying with us. We are a bit longer than anticipated, but thanks for staying with us. I would just like to thank all the presenters today for presenting your advancements so far, and also your time. So it was very interesting to see what you've all been doing during the coding phase. And but this is just for everyone else in the webinar. This is the first webinar of a series of 2. So we will have another webinar next week at the same day, at the same time on 22nd of July. And there we will present 4 additional projects who are part of the ECMWF Summer of Weather Code. And this is the projects we will present next week. They will have a strong focus on Copernicus, so different projects related to Copernicus data and Copernicus applications. And please go to our website if you also would like to join us next week and register for the webinar next week. And here just some more information. So Twitter is always a safe source if you want to have some information about ESOC, or we also have a newsletter. So if you don't want to miss any deadlines related to ESOC and also the new edition of ESOC next year, then please consider to sign up for our newsletter. And with this, I would like to thank again for everyone joining today, and also specifically the presenters. You made or you provided us a very interesting webinar today. And yes, I wish you all a nice afternoon, morning, or evening, and hope to also see and talk to you next week. Thank you. And goodbye.
Thank you all. Bye-bye. Have a good day.
Thanks, Julia.
Thanks, Julia. Bye.
Thank you. Thank you, everyone.
Thank you.